Hello dear students, this is going to be our first lecture on differential geometry. It is the course code for integrated BSc MSc is MMT604 and that for MSc is MMTC204. So the students of 6th semester integrated BSc MSc and second semester MSc, both of them can benefit from this lecture. Now in this lecture we are going to introduce differential geometry. Now in the differential geometry you have got two words, differential and geometry. So it has to be geometry which has got something to do with differentiation. Basically, in this course we are going to use the differentiation, the tool of derivative differentiation, to study the properties of the curves like curvature and many other things that we will come to know. Now, as you know, in earlier classes in your high school you did what's called Euclidean geometry, in which basically you had certain axioms that were given by Euclid, and then you deduce from those basic assumptions, postulates, certain facts, certain theorems about geometrical figures like circles and triangles, and it's all a beautiful theory actually. And for example, by assuming the fifth postulate that there exist parallel lines, or given a line you can draw another line through a point not on that line, which will not intersect the given line, you can deduce from this postulate that sum of angles of a triangle is 180. So you did things like that. Okay, we will not go there. You already have done that basically. Then you also know about what we call analytic geometry. Analytic geometry basically starts with the idea that since in a plane you can assign any point a pair of numbers x and y. So since a geometrical figure, say a circle or a straight line, is also a set of points in a plane, so we can define, or we can describe these geometrical objects by means of certain conditions, certain equations on its coordinates, on each of its coordinates x, y. For example, if you have a straight line, we know that you can write it as y is equal to ax plus b. By that, where a and b are some numbers, by that we mean that each of the points on this line would satisfy this equation. Similarly, a circle which has center with coordinates hk and radius a, all the points on the circle, I mean all the points here, can be described by the condition x minus h square plus y minus k square is equal to a square. Now this would be the equation of a circle with the center coordinates hk and radius a. So this is the stuff that you did. And not only that, you also did something called conic section. Say a conic section y is equal to x square. So this actually says that all the points on this conic section, I haven't drawn it exactly right, but you know that. And then each of the points here xy, each of the coordinates of this curve, all the points on this curve would satisfy the condition y is always equal to x square, and conversely. So in this way, you associate to a geometrical figure a condition in terms of an algebraic equation, and this is called Cartesian geometry or analytic geometry. And then you also derived certain properties of these figures and on these geometrical objects in your earlier classes. Now, what we actually want to extend the same basically. So we want to analyze, study the properties, the geometrical properties of curves, not just circles and parabola, any arbitrary curve, by means of differentiation, using the tool of differentiation. So, but for that, to make our things simpler, we don't write equations in their Cartesian form as a relationship between x and y. As you know from your earlier classes also, this equation is the same as x is equal to h plus a cos t, y is equal to h plus a sin t. Sorry, it should be k. So this equation is the same. This is called the parametric form of the same curve. Rather than having a condition, a relationship between x and y, we have a relationship of x with a parameter t and relationship of y with the same parameter t. Now if you take t any real number, it surely would satisfy our condition for the circle, and this also represents this circle. Similarly, x is equal to t, y is equal to t square would certainly satisfy the equation of the parabola for all values of t belonging to any real number, right? T being any real number. Now, now that means we can write each of these equations in terms of a parameter, okay? So, but we also know that when I say, suppose let me take the example of a circle. I've got a circle I just draw it here right now. So HK, and this is A. So it is all the points here. Every point here is satisfied by this x is equal to h plus a cos t, y is equal to k plus a sine t. So this is the parametric form, and each of the points xy here is each xy here satisfies this condition for any real number t. Okay, that means I can actually replace x and y. I can say each of the points is like h plus a cos t, y plus a sine t, right? So parametric equation then can be written in terms of pairs of numbers where this t varies. For each value of t, I will get a different point on the circle. And furthermore, we also know that each pair of these numbers can be thought of as a vector. Let me call that vector alpha. In that case, I can say that alpha is equal to h plus a cos t, k plus a sine t would be the equation of all those vectors. If I draw all these alphas starting from the origin and touching the point of the circle at some point must satisfy this equation. So this alpha depends upon my parameter t, because then I will get different points of the circle. So I can say that this alpha is a function of t. H plus a cos t, k plus a sine t. So this would be the vector form of this equation, in which basically x coordinate and y coordinate are two scalar functions, which by that scalar function means are numbers which depend upon t. I can think of it as f of t and g of t, or x at t and y at t. By that mean x coordinate of this vector and y coordinate of this vector. So that is our starting point, how we define a curve. So a curve would be a function from an interval I to Rn, basically. But in this case, just this function is basically a function from, we can talk about it as minus infinity to an interval minus infinity to infinity to R2, because all the points, all the resultant things, alpha at t would lie inside R2 in our example. And we could also restrict our domain because it repeats after every 2 pi interval. I could have also written it as alpha from minus pi to pi to R2. I would get the same set of points, the same function. So as you would see in your notes, we have defined our curve to be a function. This could be a finite or an infinite, or the whole real line interval, which lies inside R, of course, to Rn. Now that would be an n-dimensional curve, which we can't imagine, but we can certainly deal with it as a function. We can deal with it, we can differentiate it and all that stuff. Okay, so that was definition of our curve. So definition of our curve is basically a function from an interval, which could be finite or infinite, to the set of real numbers, to Rn. Basically, we are going to deal with either R2 or R3. We are not going to think about curves in Rn, but same ideas apply. So there won't be much difference what we do in R2 and R3 to if we want to translate it to a curve in Rn. There won't be much problem. Actually, there would be no problem. Now, as I said, since we want our curve, we want to use the tool of differentiation to study the curves, which we have defined now as a function, a vector function, or a function that has its codomain or range in R2 or R3 or in Rn in generally. And since we have said that we are going to use its differential geometry, so we are going to use tools of differentiation or the derivative to study the curves. So we would expect, we would impose the condition that alpha is differentiable, in fact more than once, to make any sense. And in further, when we move ahead, we might put another condition on it, that it never vanishes, for what we call a regular. We will study that ahead. Okay, now now let's start by thinking about the derivative alpha at t. What should that represent? Now when I say alpha at t, if I take this example, it is nothing but differentiating each of the coordinate functions. Yani alpha, if I say d alpha by dt as a vector function of a scalar variable, would be nothing but you differentiate each of the components. So that would be h is a constant, so it would go, so you would have minus a sine t and a cos t in this case. So similarly, if you have a function of how many, whatever the number of variables is, you just component wise differentiate each of the scalar functions as you do in calculus, what you've done in your 11th 12th. So this would be our derivative. Okay, now but if we think of this in terms of vectors, okay, so if we think in terms of vectors, since we are dealing with vectors rather than looking them as individual scalar functions, so I can think of, if I have a curve now let's take now some arbitrary curve alpha t, and let's designate, let this be the point alpha t. Basically, let us fix t at somewhere. T is some number, so alpha t would represent a point on this curve, right? Then let's take a neighboring point, alpha of t plus del t. So I just increased the value of the argument. I will get some other point. Now since I have made a small change, delta t usually denotes a small change in t, I will get a neighboring point of t, a neighboring point on the curve. So if I join these 2 points, so this vector alpha t, and when I join these 2 points, you have to think we are thinking in R3 or R2. Okay, so when this vector would be basically alpha t plus del t minus alpha t. Just that's how the vectors are. You take the vector, position vector of the final point minus position vector of the initial point. And if I divide it by delta t, so it would be, I'm just scaling it up or down depending upon delta t, basically scaling down because delta t is a very small number, right? So once I define, it would be the vector in the same direction. I'm just multiplying it by a scalar, and when you multiply a vector by a scalar, it doesn't change the direction, it just makes it longer or smaller or changes its direction. But since delta t I am assuming to be positive, so it would have the same direction, it would only scale it down. And I let this delta t approach 0, right? So when I say alpha at t, if I'm in 3 dimensions, it means nothing but x at t, its coordinates that are functions of t, because they are points on a curve, so they are functions. They change with some variable which I have denoted by t. So I would have z of t. And when I say alpha of t plus del t, it would be nothing but x at t plus del t, right? Y at t plus del t, right? And z at t plus del t. And similarly, when I take the difference, you take component-wise difference of 2 vectors. By that I mean alpha of t plus del t would be basically x at t plus del t minus x at t, comma, then same with y and z. Straightforward, nothing difficult. Then Now since I said that I would put this condition that these functions are differentiable. So if these are differentiable, I let and I divide by, oh sorry, it has to be alpha at, so let me write it again. Alpha at t plus del t minus alpha at t as vectors would be the triplet of numbers for each t, x of t plus del t minus x at t, comma, y plus y of t plus del t minus y of t, comma, z of t plus del t minus z of t. So that would be this vector. And if I scale it by delta t, it will just scale each of its components, right? Right? Because you know scalar multiplication, you would just multiply all the components by that number. Now, as I let this delta t approach 0, what would happen? So as delta t becomes smaller and smaller, my vector would be something like this. Of course, not the same length. It would just, so eventually, as delta t approaches 0, I would get a vector in the direction of tangent at alpha t. So I would define, of course, when delta t approaches 0, this would become x, this would become dx by dt, this would become dy by dt, this would become dz by dt. And I define it to be, of course, naturally enough, d alpha by dt, of course, evaluated at t. So that would be my vector in the direction of tangent at this point. And important here is that when I